In this video here, we're going to show how we can do some DC analysis, some just very basic DC analysis of these op amps here. And I've got one built here, and I'll show you how to build it, but I just want to kind of get to the end of the story here. So I'm going to do a new one here, and I'm just going to do Transient Response here. And click on OK. I don't have to worry about the timing. And I want to just show you that, hey, if we have a 0.5 in here, I can go ahead and run this. It creates a little output. It looks like there's nothing there. But if I attach a probe on the output here, it's going to give me a DC value here. And it's going to, of course, give me what the output is for this input of 0.5. And of course, we could roughly guess what it should be based off the fact that this is a 4.3 gain non-inverting op amp. So let's talk about how we build this. And I'm going to go ahead and save this. And this is actually something that I also wanted to show you because there's going to be a second video following this up called DC Sweep here. So one thing you can always do is you can actually start a new page if you wanted, but what I'm going to do here is I'm just going to delete all of this here. Let's just delete it and start with a beginning here, a blank slate. So we're going to have our place parts here. Now, one of the libraries that you need in order to simulate op amps, it's not the only one, is, of course, you might guess, is the OpAmp library. So you need to make sure you have your OpAmp library installed. Sometimes, depending on the op amp you're using, you might want to have the Texas Instrument one installed because there's a lot of op amps in the Texas Instrument one. So let's go back to the op amp. The op amp we're going to be using here is an LM741. So I'm just going to take this and plop it down right now. Now I'm purposely plopping it down because we should see here that by default it puts the positive terminal at the top, negative terminal at the bottom, and then the positive and negative power supplies here. And it also gives pins, and it does turn out that these pins are the correct pins as far as when you are wiring up the circuit. One thing I want to emphasize here though is that when we've drawn these circuits a lot in courses, we often draw it with the negative on the top. It doesn't really matter for simulation purposes. You just need to make sure to be consistent. Now, we do often do that, so you can do something called mirror vertically, and that just puts it up here. But what we should notice here now is that the negative power supply is on the top, and the positive power supply is on the bottom. So that's very important when we're setting up our simulation. All right, so we've got our op amp here. We're going to go ahead and do that non-inverting op amp, so I'm going to need some resistors. So I'll do analog, and then I will grab the resistors. And I'll need two resistors. I'll put one here and one here. I'll reassign the values here in a second. We're going to need some DC power supplies. Now, a good habit, and I'll show you how to do this here and what this is your power supplies for your op amps, you honestly don't want to connect directly up to the op amp pin. It just clutters it up. So I'm going to put two power supplies over here, V1 and V2, and those are actually going to be for the power for my op amp. And then I'm going to put one more here on the positive terminal because we're going to put a DC voltage in and see what the output voltages should be. So let's go ahead and start putting in some other components here that we need. We're going to need grounds, so 0 capsim. So I'll put some grounds here. And again, look, I'm putting plenty of grounds because I just don't want to have wires going all over the place. All these grounds are the same in the sense they're all 0 volts, but this way I don't have to have wires all over the place. Alright, done placing those. Now there's another thing here we're going to place, and these are kind of ways to get power supplies to be at different locations without always having to have batteries located all over. And it's a place power. Now, this is not actually literally placing a power. This is placing a power, I would say, reference. And so the one I like to use, you can actually use any of these, VCC, arrow, and everything. I like the VCC bar. That's just a personal preference. So I'm going to double click on that and put two of them here. Now, let's go ahead and change this here to 5 volts right now and make a few connections here. Now I'm going to rename this, as opposed to VCC bar, just to VCC. You could give it any name you want. I like doing VCC. Now what that means is if I have any other of these power connections here that are labeled VCC, they're now going to be at 5 volts, because that's what's measuring at the top here is 5 volts because it's just a battery. So for instance, if I copy this and paste it, then I'm going to use R to rotate it and move it right here, connect it up. I now have positive 5 volts connected to pin 7, which is the positive power supply for this op-amp. The advantage of this is I can have 4 or 5 op-amps maybe or more in a circuit, and instead of having to have power supplies connecting up everything and wires all over the place, I just make one little battery here for the power supply for the positive, and then I just give it a little bar here, and then I just start placing all of those at all the op-amps. So if I had a second op-amp, I wouldn't try and connect it into here. I would just copy and paste this and connect this up to my second op-amp as power. And it's going to be all the same power supply, so I don't have to worry about having wires all over the place. Makes your circuit diagrams much cleaner. So I'm going to rename this one VDD, and then I'll of course connect this up with some wires, and this is going to be my negative 5 volts, and then copy and paste that, and then I'll paste it and connect it up to pin 4 here. So we now have my op-amp powered up. Now we're just going to go ahead and connect this in a standard non-inverting scheme, and if you remember at the beginning this was a 3.3 kilo ohm because I'm going to have a gain of 4.3, and then I'm just going to run wires connecting these up with my standard feedback. And then I could put this at, for instance, 0.5 volts. Now there was one other thing here that we had. There was this red out, and that's called a net alias. And in the next video when we do our DC sweep and we talk about how to evaluate some measurements in this window here using some of the evaluate measurement concepts here, the net aliases can actually be of huge benefit to us. And you'll learn in future classes that you want to label your nets fairly regularly, just so you know what signals are where, what the outputs are, where the outputs are located. For now, we'll just call this net, and it's already there because I did it once, but you'll have to type in, I'll just call it out. And then you'll have this little box. You can't just place it anywhere. It needs to be up against a net, and a net is a wire. You know, it's a wire, and it's basically distinct wire connections here. So if I push it up against here, I now have this wire here is enabled as out. Now we could do some other things here. For instance, I could label, there's other nets here, and you can think of a net as a node. This net is essentially one node, and then here, you know, this is all one net. It's the same net, and in fact if you hover over it, it tells you what the name of the net is. If you don't name them yourself, they give them some kind of unusual names. They're N00861. Well, that's still N00861 because it's just a wire, N00861. Now if I look at this one, this net has now been labeled out, which again can give us a little bit more ability to, when we're looking at the actual results of our simulations, to be really able to track where these different outputs are and what the signals are. But we already simulated this at the beginning, and the next video is going to show you how you can do a DC sweep.